Let's move on to the second topic. This is about the computational efficiency. Recall that for a given computational problem, there are many programs that solve the same problem. In other words, programs that achieve the same goal. Recall also that the program is a sequence of detailed instructions for computation. But when we discuss computational efficiency, we will usually use an algorithm that is an outline of a program that may not be so detailed, but still mathematically precise enough. The computational efficiency greatly depends on the quality of algorithms. In other words, computers will live or die by algorithms. Let's consider one example. Here we consider the problem of computing the sum from 1 to 100. This is our computational task or goal. We can achieve this goal by adding numbers from 1 to 100. By the way, the answer is 5050. Well, this computation needs 99 additions. But is this only the way? Here is another way. We can compute the answer by two mathematical operations. It is said that the famous mathematician Gauss thought of this method when he was assigned this task in the class when he was 7. Here is how he thought. This is what we want to compute. Consider the same sum by the reverse order. Then add each vertical pair, then we get 101 for all pairs, right? So the total sum must be 101 times 100 because there are 100 pairs. Note that this total is the double of our target sum. So dividing this by 2, we can get the answer as stated here. So by this clever method or algorithm, we can get the answer by using only 2 operations. Compared with the 99 additions, this is a super efficient algorithm. Well, this is a simple calculation task, but the difference would be significant if it were some heavy computational task. The typical situation would be the case of using a supercomputer. In this case, using efficient algorithms is crucial. Otherwise, we would end up wasting the supercomputer power. So developing efficient algorithms is quite important. Oh, good point. Yes, there is no guarantee that there is an efficient algorithm. Then we may naturally ask for which problem we can get an efficient algorithm and for which problem we cannot. What sort of problems are computationally hard? This is another important subject in the research of computation. Let me explain this. First, let us look at the trajectory of research. As we studied, mathematicians like Turing identified the basic components of computation. Then this led the emergence of computers, which is like a big bang in the computer world. After the emergence of computers, they started to be used in many places. During the 60s, thanks to the advancement of electronics, such as the invention of transistors, integrated circuits, and so on, computers as hardware have been evolved rapidly. In parallel, computers as software systems have been evolved greatly. For example, introduction of new programming languages, discovery of various key algorithms, and development of basic software. This period was the first golden age of computers. Through this period, people have started facing hard computational problems. In so many areas of various computationally hard problems have been identified. Researchers found they could not come up with good algorithms. And over time, they started to feel there was a particular property common to those hard problems. To this somewhat vague feeling, around 1970, 2 mathematicians independently provided a sharp and mathematically precise interpretation. Stefan Cook from Canada and Leonid Levin from the Soviet Union, now Russia, well, I should call them computer scientists, or more precisely, theoretical computer scientists. Anyway, around 1970, they independently discovered some important fact with which they clarified what researchers felt about those hard problems. Just at the time when the mathematicians were trying to define the notion of computation, and just like different people came up with essentially the same idea independently at that time, once again, mathematicians from the East and the West during the Cold War came up with each other own but similar notions. Let us look at those hard problems. So let us look at some examples of those computationally hard problems. First example is the 3-vertex color problem. The problem asks us to color the vertices of a given graph with 3 different colors, satisfying a certain condition, which I will explain soon. But first, let me recall one important point. Remember, we studied that any computational problem is defined so as to compute some desired output for a given input. We often call an input a problem instance. In this case, the input is a graph. A graph is an object like this. It consists of vertices expressed here by small white circles and edges connecting a pair of vertices expressed here by lines. These are all examples of graphs. So they are problem instances. The input of a problem is one of these graphs. Now going back to our problem. For this problem, the input is graph. How about the output? It is a proper 3 coloring, a way to color the vertices of a given graph with 3 colors, satisfying this condition. This condition says that color those vertices so that each pair of vertices connected by an edge should have different colors. Consider this example. Suppose that this is our input graph. We want to color their vertices. Here is one coloring. Clearly, this coloring uses only 3 colors, blue, red, and yellow. This point is okay. But this doesn't satisfy this condition. Look at this edge. 2 end vertices of this edge has the same color. So this is not a proper coloring. In other words, this is an NG coloring. On the other hand, this is a correct answer, a proper coloring. You can check each pair of endpoints of the edges is colored with a different color from one another. Well, you may take a little time to check all, but it is not so difficult. In fact, checking this condition is quite easy for computers. This is what is known as the 3-vertex color problem. Let us consider another example. This is called the Hamiltonian path problem. You are once again given a graph like this, but this time the edges have directions. In this case, you need to find a way to follow the direction of the edge, a path, but do that under this condition. That is, in such a way that you go through each vertex exactly once. So the computational problem is to compute such a path for a given input graph. For example, this is one of the solutions. Number 1, number 5, number 4, number 3, 6, and 2. Taking a closer look at the graph and follow it carefully, you will see from number 1 to number 5 to number 4, number 4 to number 3, and 3 to 6, and 6 to 2 are all correspond to the directed edges of the graph. Furthermore, by this path, you went through all vertices exactly once. Again, it is not so difficult to check this condition. By the way, this problem is related to some puzzle that mathematician Hamilton proposed. So a path satisfying this condition is called Hamiltonian path, and the problem is called the Hamiltonian path problem. These two problems are representatives of many problems that troubled researchers. They may look like puzzles in first glance, but in fact, they are the extracted essence of the major problems that the researchers were trying to develop good algorithms with no success. So, what are the common characteristics of these problems? Here is the answer in one of the simplest forms. For a given problem instance, when a candidate solution is given, it is relatively easy to tell whether this candidate is correct or not. So this is the characteristics of this problem. Let's consider an example. In this problem, a problem instance is a given graph like this. Then the candidate solution is a coloring. That is a way to color vertices of this graph. Then, as we have seen, it is easy, at least easy for computers, to check whether candidate solutions like this to satisfy the condition of the proper coloring. So we can say that the three-vertex color problem has this property. How about the Hamiltonian path problem? Suppose this is a problem instance. Then a candidate solution is a way to traverse vertices like this. For this kind of candidate solution, the task of checking its correctness is to check whether each step of this path is consistent with the direction of the edges of the graph, and all vertices are visited exactly once. Again, such a check is not so difficult. So the Hamiltonian path problem has this property. A computational problem having this property is called an NP problem. Yes, clearly there is some reasoning for this name NP. But let me skip its explanation. In fact, I also skipped explaining what do we mean by relatively easy here. Of course, this condition is also specified precisely in the original definition. In a technical term, it is defined as the polynomial time computability. But please allow me not explaining this any further. The P for the name NP is also related to this definition, this P here. But let me skip its explanation. Note that these NP problems are not desperately hard compared with, say, incomputable problems that Turing and others discovered. We can check correctness of a candidate solution, and the number of candidate solutions is finite for each problem instance. So by trying all possible candidate solutions, we can eventually find one of the correct solutions. For example, you are asked to get a proper coloring to the graph here. And if you try all possible ways to color them like this, or like this, like this, or like this, then you will be able to find the proper coloring eventually in this way, so long as the graph has a proper coloring. That is, in principle, it is possible to compute the solution. In other words, we have an algorithm for the three-vertex color problem. In general, for any NP problem, we can at least have an algorithm for solving it like this. This is guaranteed by this property. However, there is a problem. The number of candidate solutions will become enormous. For example, in this three-vertex color problem, let us consider a graph with 60 vertices. Then each vertex would have 3 possible ways to color. The first vertex has 3 possible ways, the second one also, and third one, and so on. So by their combination, we will have 3 times 3 times 3, and so on. That is 3 to the 60s, this many possibilities, this many candidate solutions. This is an enormous number. If we were to check all these by a computer, even using the world's fastest supercomputer, it will take more than 1,000 years. That is to say, you can in principle compute the solution by this algorithm. However, it may be very inefficient and we may not be able to use it in general. This type of blow-up phenomenon can be seen basically in any NP problem, and it is called combinatorial explosion. Well, yeah, you may ask for a better algorithm, which is indeed a good question. This inefficient algorithm is one way to solve the problem, and actually, this may be a rather straightforward way. There may be a better way based on this. We may have a much better, much efficient algorithm. In fact, this is what researchers aimed for when they faced these NP problems. By the way, computational problem is called P problem if there is a reasonably fast algorithm solving it. In other words, that algorithm computes the correct solution easily for any given problem instance. Thanks to the advancement of algorithmic techniques, we could get reasonably fast algorithms for many computational problems. That is, we could show that those problems are P problems. On the other hand, there were some problems for which we could not think of any efficient algorithm, though they do not seem so difficult. NP problems are typical examples of such problems. During the 60s, programmers and researchers struggled with each NP problem that they encountered. Note that people did not know the notion of NP before Cook or Levin. Some clever people might have noticed this property in his own problem. Then, because of it, some of them expected that there should be a clever way to solve the problem efficiently. Cook, similarly Levin, gave a clear definition like this for this property. And what was more important is their discovery of a method to compare the hardness of computational problems. With this method, Cook, for example, mathematically proved that the satisfiability problem is the hardest problem, in some sense, among all NP problems. Richard Kopp, who was one of the audience when Cook presented his discovery, realized the importance of Cook's method and applied the method to several NP problems around him. These results had researchers realize the importance of the notion of NP and the hardness comparison among NP problems. Then it was shown that quite a good number of problems that people had struggled with, in fact, had the same hardness. In a nutshell, it was shown that they all are easy, that is P problems, or they all are computationally hard, or there is essentially no better way than checking all candidate solutions to solve these problems. Many problems that researchers had attacked individually were shown to be equivalent with respect to their computational hardness. Based on such investigations, people started believing that such NP problems are indeed very hard to solve in general, and they are not practically computable. This is called the P not equal NP conjecture. Since the discovery of Cook and Levin, the conjecture has been open. And it is regarded as one of the 7 millennium open problems in mathematics. By the way, there were some NP problems for which we could not show the highest computational hardness. In fact, for some of them, some very clever and efficient algorithms have been discovered more recently. Thus, among NP problems, some of them are P problems, that is, practically solvable problems, but the P not equal NP conjecture claims that within NP problems, there must be some problems that wouldn't be easily resolved as P problems. Since the discovery of Cook and Levin, the P not equal NP conjecture has been investigated in depth. And this research area, which is called computational complexity theory, is one of the main fields of research of computation. Well, you may wonder why we need to prove such a thing. How would discovering that NP problems like these are hard to solve make us happy? I do think there are three significant reasons to study this. First, people want to solve these problems. They are problems that came up in all aspects of our lives. For example, good scheduling is quite important in many situations in our society. Likewise, each of these problems has important applications, and we want to solve them anyway. Of course, if P is not equal to NP, then we cannot hope for a perfect algorithm for them. Even so, our desire is to solve something or anything, whether they be individual or partial. Therefore, studying the difficulty itself like this helps us understand what aspects can be conquered and what types of partial problems could be more easily solved. It is for this reason that it becomes important to know where the difficulties lay and what is causing it to be practically unsolvable. The second one is more direct reason. In fact, the hardness of some NP problems is the basis of the public key cryptography. Let us recall the computational task of cryptanalysis. It is obtain a plain text M from a given ciphertext C only. In the public key cryptography, this task is indeed an NP problem. To see this, consider that you are given a candidate solution M prime, that is a candidate of the plain text for the ciphertext C. You can check its correctness by applying encryption to this M prime with the encryption key P. Checking it produces the ciphertext that you want to decrypt. Recall that this key P is a public key that is known by everyone. So everyone can check whether M prime is correct or not easily. So this is the property of NP problems. Thus, the computational task of cryptanalysis is indeed an NP problem. So the hardness of this NP problem is important. Do you remember? When we discussed the security of cryptography, I explained that the security is guaranteed computationally. This is in fact the computational hardness of this NP problem. So in this case, we really want that the problem is not solvable even partially. As I have mentioned a moment ago, there are those who wish to solve problems even if it were partially. But what I'm saying here is that there are times it is better to not have that resolved even partially. Actually, this is why we need to understand the hardness of NP problems more. By the result of Cook and Levin, we roughly know that all top NP problems are equally hard. But if we consider more carefully, there should be some difference among the hardness, and this difference could be significant for our daily life. The third motivation is for understanding the nature of computation. Investigating the P not equal NP conjecture is to study the limits of algorithmic efficiency. It is similar to the time when mathematicians studied the computability, the limits of computation, which led the emergence of computers. In the history of mathematics, a breakthrough idea has been discovered or a new theory has been established from time to time through the research of impossibility. Similar achievements have been established from the research of the limits of algorithmic efficiency. Let us see the trajectories since the discovery of Cook and Levin. As I mentioned, the hardness of NP problems are quite related to cryptography. In fact, the notion of public key cryptography and its basis have been established in computational complexity theory, which became the basis of cybersecurity. Then, computational learning, again another topic related to NP problems, has been proposed, which became the basis of various learning algorithms and the field called machine learning. In 1990s, the randomness in computation has been studied extensively again in computational complexity theory, which provided some key technologies in statistical algorithms used in big data analysis, which is now used a lot in data mining. In summary, our desire for resolving the P not equal NP conjecture has been a driving force for the development of the current ICT society. Note that the conjecture is still open, and actually, we don't have any clue for resolving this conjecture. In other words, there are still many mysterious things about the nature of computation. So if you like, please jump into this attractive field.